Hey everyone, this is a supplemental video for project part 4. In this part, I'm asking you to run an ARIMA model for the company revenue data. I want to show you the steps that you're supposed to follow. I also want to show you 2 examples. The first example is a typical one in which when you get the autocorrelation and partial autocorrelation graphs, you find one is cutting off and the other one is dying out to a certain extent. In the second example, when you got autocorrelation and partial autocorrelation, you will find that it is very hard for you to determine the specification for the ARIMA model because you can't tell which one is cutting off and which one is dying out. And you can't even determine the specification because most of the lags at the lower levels are insignificant. So I want to show you what you can do in those situations. And then you can decide which situation your data shows and go from there. So the first example is from JetBlue Airline. I've got the revenue here. The first step is to get the seasonally adjusted data because we've got quarterly data. And in this project, I didn't ask you to run the ARIMA seasonal model. The main reason is that the seasonal ARIMA model we talked in the lecture and in the exercise are relatively easy ones. In practice, the model can be much more complicated. So we won't be using seasonal ARIMA model. So the first step is to go to stat, time series, go to decomposition, variable is revenue, JetBlue revenue, seasonal length will be 4 because this is seasonal data. All right, so you need to look at the data to use the right seasonal length. If it's quarterly data, it's 4. If it's monthly data, it's 12. It's not always 12 or always 4. It depends on what kind of data you have. Then we go to storage. We want to store seasonally adjusted data because that will be the data we use for the ARIMA model. So click OK. OK again. In the third column, we've got the seasonally adjusted data. The SEs represent the seasonalized data. Okay. The next step is to examine if the seasonally adjusted data is stationary or not. My guess is not, because for revenue data, we usually expect an upward trend. So I will go to time series plot, pick seasonally adjusted data, click OK. There we go. We can see very clearly there's an upward trend that is almost a straight line, very strong trend. And therefore, we need to take the difference first before trying to specify the ARIMA model. Apparently, for the integrated part, we have an I1 process. So let's do the difference. And I recently discovered there's an easy way to get the difference. You go to stat, time series, differences. The series will be seasonally adjusted data, and we want to store the difference in div. This time, we don't need to name the variable before we click on the buttons. And we are taking the difference at the first leg. So we're leaving 1 for the leg. Click OK. That's the difference. Basically, for each number is the value for that quarter minus the value for the previous quarter. Okay, so 9.142 is equal to 145.64 minus 136.5. Then let's look at the autocorrelation and partial autocorrelation graph to determine the specification for a ARIMA model. You might say, well, don't you need to verify whether the data is stationary or not before you do that? Yes, I could. I could get the time series plot and examine whether there's still trend. On the other hand, when I get autocorrelation, for the autocorrelation, I'm gonna get the difference data. I will also be able to tell whether there's trend or not, because I will observe there is very clear pattern that the lags are declining gradually, and for the first couple of lags, they are significant, which apparently is not the case I have here, and therefore I can tell I don't have trend anymore. So that's the autocorrelation function. Let's get the partial autocorrelation function as well. Then we can determine the specification for the Riemann model. Partial autocorrelation. Still, we are using the difference data for the partial autocorrelation graph. And that's the partial autocorrelation graph. I would say these two are kind of similar to each other. However, for the partial autocorrelation, the first leg is significant, apparently, but the second leg is almost zero. So I'm gonna determine that the partial autocorrelation is cutting off. Going back to autocorrelation graph, the first leg is significant, but then it turns to be positive. In that sense, I would say the autocorrelation is dying out. And therefore, we have autocorrelation dying out, partial autocorrelation cutting off at leg 1. That indicates an AR1 process. If you look at this slide, it shows that when autocorrelation is dying out and partial autocorrelation is cutting off, we have an AR process. Since in our data, partial autocorrelation is cutting off at leg 1, we are looking at an AR1 process. So back to our example here, we determined that the autocorrelation function is dying out and the partial autocorrelation is cutting off at leg 1. Therefore, we are looking at an AR1 process. And if we write it in ARIMA, so we have ARIMA 110. So now let's fit the ARIMA 110 model. We're gonna go to Stat, Time Series, ARIMA. Notice that for the series, we will use the seasonal adjusted data. We don't use the difference data because we're gonna take the difference within the model by putting 1 for difference, and we're putting 1 for autoregressive. Let's get the residuals since we'll check it at the end. So click on OK. That's the AR1 model. Now MS is 1352, not too big. In terms of the p-values for the Box-Pierce test, all of them are higher than 5%, so we can tell the model is adequate. Now, as a last check, we're gonna look at the residuals. Let's get the autocorrelation for the residuals. So here's another situation you might see for your example as well. That is, although for the p-values in Box-Pierce test, chi-square test statistic, all of them are higher than 5%, meaning that our model is adequate. But when you check on the residuals, you will find for the autocorrelation function, it is significant at a certain lag. For our case here, it's significant at lag 11. At this point, there's really nothing we can do about it. With our limited cover of a Riemann model, we will just notice this significant lag. And sometimes such significant lag may just due to some random correlation. It may not represent anything systematic. So overall, we'll say the ARIMA 110 model is adequate for our model, and we can use it to do the forecast. For forecasting, we'll need to rerun the model. So we're gonna go back to Stat, Time Series, ARIMA, and click on Forecast. We're gonna supposedly forecast for the next 2 years, but in the project, I put 2 periods. So we're gonna put 2 periods, otherwise it's supposed to be 8 periods, that's for 2 years. Click OK. Okay again. And that's the forecast for the next 2 periods in this table with a 95% confidence interval. In this example, most of the time for the autocorrelation function and the partial autocorrelation function, we see our typical ones in which we can judge which is cutting off, which is dying out. Next, I'm going to show you another example in which it is hard for you to determine which one is cutting off and which is dying out, because for the lags at the lower levels, none of them are significant. The example I have is the TiVo revenue. The first step is to make it seasonal adjusted. So we want to go to stat, time series, and use decomposition where the seasonal length should be 4. And make sure you store seasonal adjusted data. Click OK. OK again. And in this column, that's the seasonally adjusted data. We're going to use this data instead of the original revenue data. Then, as usual, we will start with a time series plot to examine whether the series is stationary or not. So we go to stat, time series plot, and pick seasonally adjusted data. So click OK. And that is the time series plot. We can see that even after adjusting for seasonality, there's still trend and some pattern that seems like seasonality, but they are not. They may be other factors that are affecting the time series, making it moving up and down. Since we can observe trend, then we need to make the data stationary by taking the difference. So we go to stat, time series, and there's differences. When you click on it, so we'll select the seasonally adjusted data. Then, as usual, I will name it as diff. We are taking the difference at lag 1, so we will leave it as default and click OK. And that's the first difference data. Okay, and this data should be stationary. Let's double check that. We go to stat, time series plot, click OK. And this time we're looking at the difference data to see if it's stationary or not. So there we go, that's the time series plot. This time you can tell clearly that the time series is evolving around a constant mean. That means this time it is stationary. We don't observe any particular trend. We don't observe seasonality either because we already adjusted the data for seasonality. So the up and downs you see, it's not from seasonality. So let's get the autocorrelation and partial autocorrelation to determine the ARIMA model specification. We're going to use the difference data. Click OK. That's the autocorrelation graph. Okay. And then we'll go back to stat, time series, partial autocorrelation, still do difference. Click OK. This is the partial autocorrelation function. All right. So what you see in these two graphs are almost completely different from what we observed in the lecture. Okay. In the autocorrelation function, I don't observe any significant lag. I can't tell whether it's declining or it's cutting off because nothing is correlated. In the partial autocorrelation function, I don't observe any significant autocorrelation either until these two. Okay, but they are at lag 16 and 18. And since this is correlate data, it is not easy to explain why the series will be related 6 periods ago. Like for example, your current period revenue is related revenue 4 years ago. That's probably wouldn't make much sense. And therefore this significance we observe at lag 16 and lag 18 is probably due to some random error out there. Okay. And for partial autocorrelation, we can't tell whether it's cutting off or dying out either because nothing is significant at the beginning. And this just indicates a Riemann model may not be useful or helpful in predicting TiVo revenue. So what do you do with this situation if a Riemann model is not appropriate for your data? Well, to complete the project, I would suggest that you try AR1 process and MA process. So let's do that. So go to Stat, Time Series, ARIMA. The series will be the seasonally adjusted data. So we will put 1 for difference. And let's try AR1 first. So we put 1 for autoregressive. And let's get the residues, since we're gonna check it. And that's all we need. Click OK. So this is ARIMA 110. What we see here is that MS is 289 and all the p-values are higher than 5%. So the model is adequate, although when looking at the autocorrelation and partial autocorrelation, we decided ARIMA may not be appropriate for it. Then let's check the residues. So we go to Stat, Time Series, and do autocorrelation for the residues. And the residual also shows that the model is adequate. We don't observe any significant autocorrelation. That's the AR1 process. Let's do the MA process. So similarly, we go to Stat, Time Series, ARIMA. And it's still similarly adjusted data, but this time we're gonna put 0 for autoregressive and 1 for moving average. Click OK. That's the other one. And MS is 288. The other one is 289. So they're very close to each other. And this time, all the p-values are also higher than 5%. And the model is valid. Let's double check with the residues. So we'll go to Stat, Time Series. And we want autocorrelation for residual 1. As expected, we don't observe any significant lags, all right? So both models are adequate and the numbers are very close. The MA process is slightly better than the AR process. I would suggest that you pick MA1. However, it wouldn't count it as wrong if you decided to use AR1 process because the difference is so small. So that's the first relation. Now, when you look at your autocorrelation function for the difference data and you don't observe any significant autocorrelation, or you observe some significant autocorrelation, but they are in a much higher lag, like 16, 18, or even I would say at 8 or 10, we don't have that here, but for some of the situations, you may observe significant lags at 5, 6, 8, or 10. I wouldn't suggest you to use AR6, AR10, or MA6 or MA10, because when you include AR10, that basically means you included 10x variables. That's tons of noises introduced to the model, and which will make the model rather useless, actually. Remember the principle of parsimony. We prefer simpler models to more complicated models, right? So if you have similar situations, go ahead and try AR1 process or MA process. So the model you're gonna be trying will be ARIMA 110 or ARIMA 011. Of course, I'm assuming your data shows trend at the beginning And I believe for most revenue data at Unsigned, there will be some kind of trend, okay? So you can try these two models and go from there. All right, so that's the two examples I want to show you. If the revenue data you're working with shows something different from the two I just discussed, just feel free to send me an email with the screenshot of the graphs. I can take a look and give you more suggestions.